Good morning, everyone. My name is Diego, and today I will present a detailed critical review of the article entitled Performance Evaluation of OLSR and AODV in VANET Cloud Computing. This work was developed for the Computer Networks course at the Federal University of Pará and involved the collaboration of my colleagues Bruno, Diego, Emmanuel, Taina, and Yasmim. Our goal here is to discuss how routing protocols behave in a highly mobile scenario, such as vehicular networks, and to critically analyze the methodology applied by the authors of the original article. To provide context, we need to understand what VANETs, or vehicular ad hoc networks, are. They are an evolution of common mobile networks, MANETs, but with very specific characteristics. In a VANET, the network nodes are vehicles and fixed roadside infrastructure that communicate without the need for a mandatory centralized base. They form the basis of intelligent transportation systems. Unlike a home Wi-Fi network where devices are stationary or move slowly, in a VANET the nodes move at 60, 80, or even 120 kilometers per hour, which requires the network to be able to self-configure in milliseconds. The applications of these networks are fascinating, ranging from road safety, such as sudden braking warnings or accident detection, to passenger entertainment via cloud computing. However, the environment is extremely hostile to the network layer. We face the challenge of high mobility, which causes what we call dynamic topology. The path a piece of data travels now may no longer exist in half a second. Furthermore, we face shadowing caused by buildings and other large vehicles, which generates constant connectivity failures and demands very robust routing protocols. The central focus of this study is the comparison between two classic network layer protocols. First, OLSR, which is a proactive protocol. It attempts to keep a network map always up to date through periodic messages. The major difference of OLSR is the use of multi-point relays, or MPRs, which are nodes selected to reduce control traffic, preventing network congestion. On the other hand, we have AODV, which is a reactive protocol. It does not maintain constant tables. It only discovers a route when there is a real need to send data. In our analysis, we highlight that this choice defines the network delay. OLSR delivers the packet faster initially, while AODV saves bandwidth by not sending unnecessary updates. When analyzing the physical layer, the article uses the IEEE 802.11p standard specific to vehicular environments. But the point that deserves the most attention is the propagation model. The article compares the two-ray ground model, which is simplistic and only considers the direct signal and the signal reflected from the ground, with the Nakagami M model. The Nakagami model is much more realistic for cities because it is probabilistic. It takes into account signal fading and the multiple reflections that occur in dense urban areas. For network design, understanding that radio signals do not behave perfectly is crucial to avoid unexpected packet drops. To perform this evaluation, the authors used a co-simulation technique. They integrated Sumo, a microscopic traffic simulator that moves cars according to real traffic rules, with NS3, the gold standard in network event simulation. This integration is done via trace-based mobility, meaning that the real movement of cars in Sumo generates a file that feeds into NS3. This ensures that the network results reflect what would happen at a real intersection and not just in a static laboratory scenario. Here we detail the test scenario, a 200 by 200 meter urban intersection with 32 vehicles. Data transmission was performed using the UDP protocol with a constant bit rate, CBR, and 512 byte packets. An important detail is that the researchers varied the transmission rate from 100 kilobits per second to 800 kilobits per second. In our review, we pointed out that although 32 vehicles is a good starting point, this number is relatively low to represent the network congestion that occurs in large metropolises, where hundreds of devices would be competing for the same radio channel. Analyzing the throughput results, we observe an interesting behavior. When the network load is low at 100 kilobits per second, the two protocols behave almost identically. However, as the load increases to 800 kilobits per second, AODV begins to show slightly superior performance to OLSR. This happens because the overhead of OLSR, those constant table update messages, begins to compete with the actual user data. In network stress situations, the reactive protocol ends up being more efficient because it is more silent when it doesn't need to act. This table illustrates the devastating impact of signal fading on the network. When we switch from the ideal model to Nakagami's realistic model, the maximum throughput drops drastically, and the packet delivery rate, PDR, suffers significant degradation. This shows us that in the vehicular network layer, packet loss occurs not only due to congestion, but also due to the unstable nature of the wireless channel itself. For safety-critical applications such as automatic braking, this variation of up to 30% in packet delivery can be the difference between system success and failure. In our critical analysis of the work, we summarize that the article successfully demonstrates the fragility of VANETs in the face of realistic propagation models. However, as experts in training, we noted some shortcomings. We missed the measurement of end-to-end delay and jitter, which are essential metrics for video streams or real-time control. Furthermore, the 50-second simulation time is too short to guarantee that the system has reached a stable state. Our criticism is that for future networks, traditional protocols such as OLSR and AODV need cross-layer adaptation mechanisms to survive in the urban environment. In conclusion, this study reaffirms that there is no perfect routing protocol for all situations. OLSR is excellent for route readiness, while AODV is more resilient under high traffic loads. The biggest lesson we learned is that vehicular network planning must focus intensely on robustness against signal loss due to obstacles. The next step in this area of research certainly involves the use of software-defined networks and artificial intelligence to manage these routes predictively.